Alright, now we want to find that the heat predicted to be lost, so the same sort of thing, when the mass of sodium hydroxide in question 43 is hydrated. Okay, so this is where we're applying Hess's law. This last part, we're looking at Hess's law. So here's when we did it on our own. We measured the reaction between HCl and NaOH directly. We put the solid NaOH in the acid solution, and that's a combination of the hydration, where we dissolve the NaOH, and the neutralization, where the NaOH neutralizes the HCl. Okay, so here we did that complete process, and here we are doing it according to the parts that we did above, where we hydrated it and we neutralized it. We just need to account for the fact that we used a different mass. Okay, so we're going to use the mass from question 43. All right, that's here. This 2.1493. That's the mass we're going to use, and we want to find out how much heat would be lost if I used that amount and I hydrated it. Okay, so I'm going to go back to the top and reference my heat of hydration. Okay, so at the end of this section, I calculated the heat of hydration in joules per mole of sodium hydroxide. Okay, now, so what I need to do is take this value, negative 40,300 joules per mole, and multiply by the moles of sodium hydroxide I have from 43. Okay, so I need to convert this to moles and then multiply. Okay, so here's my grams. Let me first find the moles. So I have grams divided by the molar mass, which is 30.99. So there's my moles of NaOH. Okay, now here was my heat of hydration in joules per mole. Okay, that was the 40,300, and I'm going to take that joules per mole and multiply by my moles. Okay, and at the same time I need to convert that to kilojoules, so I'm going to divide by 1,000. Okay, so 2.16 kilojoules is the energy that was given off, so it's going to be negative, but 2.117 if I round that. Okay, so the kilojoules to be lost, so it's negative 2.17. Okay. Next, the heat in kilojoules predicted to be lost when the mass of sodium hydroxide, again, like I said, we're pulling it from the neutralization part. So here we did it from the hydration part here. Now we're looking at the neutralization part from here, where I take that solution and that's why I found this value. Okay, and I can use actually either one of these. They will give me the same result. joules per gram of sodium hydroxide or joules per mole of sodium hydroxide, it'll work the same way. Okay, so that's the heat of neutralization, and what I want is, just like I did with the previous one, I'm going to multiply by either the mass of sodium hydroxide if I use this one, or the moles if I use that one. And I'll go ahead and do both so you can see that they're the same. Alright, so running out of space here, but let me just put it in the middle here. Okay, so here I have this 1582. That was my heat of neutralization. It was negative, but I'll take account of that in the end. And that was joules per gram. Okay, so I would just multiply that by the grams to get my joules, still dividing by 1,000 to convert to kilojoules. Okay, so there's my kilojoules from the neutralization. And just to show that that is in fact the same thing, if I use the joules per mole, the 63,300, and I multiply by my moles, you'll see you get the same thing once I divide by 1,000 to convert that to kilojoules. Okay, so 3.40 is what I get here. Alright. Well, let's see. Oh, I forgot that this is loss of heat. So that will be negative 3.40. All right. And now we want a percent error. All right, so when it's asking for the percent error, what it's asking for is, see, we're testing out Hess's law. Here, we're combining the two processes. There's the hydration and there's the neutralization. Okay. First, we did a reaction. The first part of the lab, we hydrated the sodium hydroxide, where we dissolved it in the water. That was the hydration. And then we did a neutralization, where we took that hydrated sodium hydroxide, the dissolved solution, and we neutralized some acid with it. Okay? So that was my neutralization. But in this part, this last part of the experiment, I'm doing both of them together. I'm putting the solid directly in with the acid, and that's the combination of both of these parts of the lab. Okay, so when it's asking for the percent error, it's wanting to know, okay, what's the difference between, because Hess's law should say what I get here, since that is both of these put together, if I add these two values, I should get this value. Okay, and so the percent error is the error between these two values, which is what I'm testing. So that's my experimental. That sum would be my experimental, and then this is what I'm going to use as my actual, because that's what I actually got when I did this. Okay, so the sum is that 3.4 plus the 2.17. Okay, and we're not worried about the signs because it wants a positive value, and so we're just going to make it positive in the end. All right, so there's my experimental. Now my actual is from the the 3.5, okay, which I had it in joules here, convert that to kilojoules, and then it's 3.5 like I entered, and that's what I'm going to be using as my actual value. So the percent error is the experimental minus the actual divided by the actual times 100%. So 59.2% is, that's my percent error, 59.2. Okay. So there you go. That finishes off the calculations part, except for one little question.